My name is Brian Avenel. I work at National Instruments in a hardware design engineer, hardware design engineer, and I work in the SDR group. So this morning's talk is going to be it's labeled Managing RF Spurs, but really it's going to be a survey. Sorry. It's going to be a survey of various RF architectures that we might see in software-defined radios, and I'm going to use spurious response as the way of comparing and contrasting them. So I'm going to go through some trends that I see in RF architectures. I do have a little bit of a refresher course I have to go through in order to get to the bulk of the conversation, which is going to be outlining these 4 different transceivers. So the trends in modulation complexity I look at as the combination of bandwidth and the number of bits per symbol. And over time, of course, it's been increasing. And as we get into new standards like the 5G new radio spec, not only is the modulation complexity increasing, but it looks like it's accelerating. So it could be that the software-defined radio architectures that we're capable of supporting today's standards might need to be relooked at as we get into the more demanding dynamic range requirements going forward. So what I see right now is the vast majority of our software-defined architectures are direct conversion or IQ, and with a small subset being super heterodyne. This has served us quite well, especially over the years when the data converters were limited in bandwidth and their price. I mean, that we could get a wider bandwidth type architecture. There we go. At affordable price. But there's some trends happening right now in both RF components and actually the data converters themselves are allowing the data converters are getting higher sample rates and their cost structure is coming lower, which is now going to allow us to start entertaining some RF architectures that were probably previously a little bit not cost a little bit cost prohibitive to use. So super heterodyne, single sideband, and low IF. So this is a possible trend, but even after that, the majority will still be direct conversion in my view. So this is what I'm here to talk about is if we start seeing some of these newer architectures, I kind of want to walk through them and look at their pros and cons of each one. So here's the little refresher portion. I'll try to keep this brief. I hope it's not an insult to a lot of these people in this room. I already know this, but I'll keep this quite brief. But I want to use this so I have the same kind of language when I walk through all my receivers. So sampling theory. Take an analog signal, you go through a data converter at a simple sample rate, and it creates discrete samples. Nyquist says that we've got to be sampling at twice the bandwidth of what you're trying to measure. And when you do that, you can break this up into several Nyquist zones, a frequency into Nyquist zones. And this gives you 2 pieces of information. One is it tells you what is the maximum bandwidth, that's fs over 2. But it also tells us where we can place the energy in which spectrum. We can't have energy that will overlap multiple Nyquist zones. You have to keep everything within one Nyquist zone. If you happen to do that, then you'll get what's known as aliasing. So for instance, in this case, I'm interested in operating in Nyquist zone 1, but I happen to have something in Nyquist zone 2. It'll alias over or fold over, or after the sampling process, it'll appear as it is coming from Nyquist zone 1. The way to mitigate that is you add a filter, an analog filter, an anti-alias filter to suppress those unwanted tones. But being analog, it's got some practical limitations of its bandwidth is maximum about 40% of the sample frequency. Next in my list of refreshers is mixing theory. Mixing theory, at the very fundamental thing, you can think of this as multiplying 2 time domain waveforms. And if you go through a simple trig identity, you'll see that one tone will get broken up into a sum and a difference tones. If one of the signals has got modulation on it, then you'll be frequency shifting both a sum and a difference kind of direction. Keep on going. Negative frequency representation. Now, this is a mathematical construct, but it's necessary for us to be able to analyze direct conversion receivers. So if we go back to Euler's identity, you can take a cosine wave and break it up into 2 complex phasors. And if you plot those on the real and imaginary axis, you'll see that those phasors are rotating in opposite directions. We say that the counterclockwise is positive frequency rotation, and the other one is negative frequency rotation. A sine wave is got a J operator applied to it, and if you map that onto the real imaginary axis, it just merely presents a 90 degrees phase shift. But you still have two vectors that are rotating in opposite directions. If you put that into our frequency domain, you'll see that you'll break it up into negative and positive frequencies. A cosine will have all real data, and a sine will have imaginary data, as shown here. And one last one, my refresher, is a representation of a real signal. A real signal is a signal that can be broadcast either over the air or down a cable. And it also has to be represented with negative frequencies. And one of the things that exhibits is it's got even symmetry for the magnitude and odd symmetry for the phase, as shown on this diagram. Okay, that's it. So the next one, now we start walking through the receivers. And I'm going to start with direct conversion, because that's probably most familiar, and that's what's most readily in the diagrams now, or in the architectures now. So we have transmitter and a receiver. They're mirrors of each other. Once you understand one of them, it's easy to apply the same principles to the other. So I'll be primarily focusing on the receiver. So the beauty of the direct conversion is its simplicity. It's got one frequency conversion stage, the IQ demodulator in the receiver case, one LO, and I'll be showing later on, a very limited need for RF filtering. So it's quite compact, cost efficient, and all that. The way it works for the receiver is you have some RF energy coming in, and you'll tune your LO to the center of that RF energy. And what that will do is it will mix down to the I and the Q paths, the in phase and quadrature phase paths. They'll both get sampled. Once it's in the digital domain, there'll be some reconstruction going on, as shown, to get a representation of what the input signal was. All right, so to me, one way of describing the behavior of the IQ process is graphically. So that's what I'm going to do instead of equations. And showing right here on this side is the I path. So the real signal coming in from the RF input signal is that yellowish trapezoid. And then in the I path, I'm going to be mixing it with a cosine wave, as shown. So from the frequency translation process, we'll get two copies. There'll be a sum and a difference from both the negative and positive sides. And we'll filter off the summation, so you're just left with what's down at baseband. And you'll see at this point that the energy from the negative and the positive sides are on top of each other. And we'll fix that. So now I'll go through the same kind of process for the Q side. And the only difference is now I'm multiplying it by a sine wave. And that will take our RF input signals and make them imaginary. In signal processing, I will apply a Hilbert transform to the Q data. So I'll be rendering all those imaginary information into reals. And what you'll see is down here, all these tones or signals are real. And the information that came from the negative axis will actually cancel. And the information that came from the positive axis will add constructively, and what you're left is a reconstructed signal of what your input was. So in the sample domain, what you'll see is something like this. And there's a couple surprises. One is it straddles two Nyquist zones, which we kind of said that's not something you should be doing. Well, it turns out that the I and the Q paths that made this up, we're both within the Nyquist zones. So it's only the reconstructed digital signal that is looking like this. And then the other one is it doesn't exhibit even symmetry. Well, it's a complex signal, so it doesn't have to follow the same rules as a real signal. Okay, so far the analysis is being used perfect hardware. The I and the Q paths are perfectly balanced, perfect amplitude and phase matching. The quadrature had perfect 90 degrees phase shift. So now I'm going to start walking through what happens when things aren't perfect. And the first thing is IQ imbalance images. You put a tone in one side of the spectrum, and you'll get a copy of it on the other side. And the difference in amplitude is the image rejection. This can be explained just by the gain and phase differences between the I and Q path. You can construct a simple model that you just apply those gain differences into the Q path as shown, and go through a bunch of algebra, and you can come up with a closed form equation and use that to do this plot. So this plot shows phase offset is the x-axis, image rejection on the y-axis, and then each line is a different amplitude imbalance. And you can see here, 1 degree is a phase shift difference between the I and Q paths, and 0.1 dB of amplitude difference, which are actually quite small, gets you 40 dBc of image rejection. So our data converters these days are capable of 70 or 80 dB of Spurs-free dynamic range. So we've right now kind of destroyed our front end with this device. So the good news is that we can apply digital corrections. You have to do a calibration process, and you can undo the effects of this. But to get down to the 70s, which is off this chart, we're now talking about phase differences that are sub-10th degree and amplitude differences that are sub-100th dB. So yes, you can do it. It can be done, but it's very dependent on, it's very temperature sensitive. And it's akin to, one of my colleagues says, it's like balancing a bowling ball on a pin. Yeah, you can do it, but it's not easy. So you can, that's how that works. The other, the consequence of having these poor images, they lead to poor EVM. Here I'm showing a 30 dBc image on the left side, and it'll lead to, no better than 30 dB of EVM, or 3%. So that's the direct consequence. The other distortion, one other distortion I want to talk about is the DC offset. LO feed-through is another term that you use to apply, but it's right in the middle of that spectrum, right at 0 hertz, you'll see a tone. And if you paste together several of these to create a multiple spectrum, you'll see like a picket fence effect. How that is explained is the DC offset. DC offsets. We are going to baseband. Any kind of amplifiers will be op-amp type devices. They will have some sort of offsets. Just a few millivolts is enough to offset this LO feed-through term. The data converters will have DC offsets in there. And there's one more mechanism. The LO can leak out, reflect off front-end components, come back into the IQ demodulator, mix with itself. It mixes right down to DC, which is, or 0 hertz, which is DC. So again, you can counteract this with digital correction in the signal processing, but the same caveats apply to the IQ imbalance. It is temperature sensitive. And it requires a calibration process to be able to measure what the DC offsets were so you know what to apply. Other spurs to worry about. Intermods. Second order intermod is especially a problem with these kind of architectures. You got 2 tones, and their frequency spacings, if it's within the bandwidth of your receiver, you can generate a signal. These are generated in the front-end components using amplifiers and mixers. So you could be looking at a whole portion of the spectrum away from these tones, and they'll still come in and create a tone that you'll see. These could be 2 radio stations that are this far apart to create this, if you're doing an over-the-air type thing. So as the bandwidths are starting to increase to support these new radio standards, you can see we're going to be allowing more and more of this kind of behavior to leak into our front end. So our narrowband radios from before, now as they're going wider and wider, we're going to see more of this effect. Another distortion mechanism is harmonics. The baseband has an infinite number of octaves. You just can't filter out the harmonics. So now we're solely dependent on whatever amplifiers and the data converters we have in the IQ path, in the baseband paths. And here you can see I've injected a fundamental tone, and you can see the second and third harmonics are there. And then their images leak over if I'm not doing any kind of image suppression. So the direct conversion is the good is low parts count. It's small, very cost efficient, and simple RF filtering. I didn't even really talk about that, but there is not really a major requirement for a lot of RF filtering unless you want to just get rid of the out-of-band type stuff. So of course, The bad is that you do have those IQ images and DC offsets. Could require some sort of a calibration to get rid of them. And it's also prone to intermod distortion as well as harmonic distortion. Okay? So the next architecture I want to talk about is low IF. Low IF has the exact same architecture as the direct conversion. The only difference is instead of tuning right into the middle of my signal of interest, I tune just to the outside of it, shown by this F sub C, which is where I'm going to be tuning it to. And when you do the same kind of analysis as you did for the direct conversion, you'll find in the sample domain that the signal occupies only one of the Nyquist zones. So things like the images that are on the other side are not in band. The DC offset is not in band. So that's the advantages. The disadvantages is that we are half the bandwidth of the direct conversion. But I mentioned earlier that data converters, their sample rates are growing and without a significant cost increase. So what was a disadvantage before, we might be able to recover from this this bandwidth problem by using a higher sample rate data converters. So I think it's a trend that we could start seeing more of these kind of things. So yeah, that was my comment right there. So this architecture works really well for receivers. The images and DC offsets are filtered out. You don't see them. But for the transmitters, they're still present. And in fact, especially on the LO feed through, not only like on a receiver, you can have some reverse isolation of the amplifiers to get rid of the LO feed through. Here, we actually amplify that out. So here I'm showing a measurement I made where I put two signals in one Nyquist zone, and you can see its images and DC offset are there. So for a transmitter, when you want to have a nice spectrum, or you got to meet some sort of spectral emissions mask, you'll probably still have to go through the same kind of IQ imbalance kind of a calibration procedure to get that down. But the nice thing is the images and DC offsets do not fall in band, so you're not causing any kind of modulation metric problems. You're just causing more of a spectrum leakage type of problem. Okay? So the good, same kind of comments about the direct conversion. In fact, we can use, for another advantage is you can use exact same hardware for direct conversion. So you can either operate in wide bandwidth mode or go to the low IF mode to get better performance. And the no in-band IQ images and DC offsets to worry about. But we do have a reduced bandwidth, but I kind of said that we are starting to see higher sample rate data converters, so maybe we can overcome that impediment. And for the TX, well, you still have those DC offsets and images, so that could be an issue. Okay, so those are direct conversion and low IF. I'm next going to go to the super-heterodyne. The biggest difference between a super-heterodyne and the direct conversion is that instead of mixing down to baseband, we're mixing down to some sort of an IF. So now I'm AC coupled, don't have any of those DC problems to worry about. So super-hets come in a couple different flavors. We have single stage, multiple stage. In fact, we can even have super-het added to direct conversion. And we see some of this in millimeter wave type things. And sometimes they will refer to that super-het stage as a block converter. But so we'll take maybe millimeter wave type of frequencies, bring it down to some sort of lower type of IF, and then use IQ to do the rest of the processing. Okay, to describe the behavior of this, I have to go back to my mixing equation. Before, I had a very simplistic mixing equation. Here, I'm adding a little bit more detail to it. You send in pure tones into our mixers, no harmonics on the RF and LO. And inside the mixer, you'll be generating the harmonics in both the RF as well as the LO. And that's depicted by this mixing equation off to the left over there. Any combination of the those harmonics that fall into an IF passband will be a spur. And so right here I'm showing is a desired mixing equation, which in this particular case is a -1,1 type of performance, and shows that if I have my RF energy 1 IF away from my LO, they'll mix down to my IF, and that's what you want. Images, these are mixer images, are one class of spurs, and we just invert the signs on the M and N on this one. But what it really says is that blue blob of energy over there, if it's 1 IF, they'll both, the desired as well as the image will mix down to IF, and if you got energy on both sides, they'll clobber each other. Or suppose you only have energy on the, one blob of energy. At IF, you won't be able to tell, is that the real image signal or is that the image? Way to mitigate that is to add RF filtering. And here I'm starting to show some of the disadvantages of the Super-Het structure is that we do need more RF filtering to rule out some of these undesired tones. So that was, as the image is one class. So here's just the general M N Spurs, and I'll demonstrate here. I'll make M in N 2 minus 1. And in this particular case, I'm interjecting a tone, a fundamental tone, at 600 megahertz, and this 2-1 happens to create a spur at 1 gigahertz. I have another tone just right next to it, and from this viewpoint, you would be hard-pressed to tell which one's the spur and which one's the tone. One mitigation technique is that the amplitudes of the spurs will drop by the order of the RF harmonic, M. So in this case, it's a second order type of thing. And if we drop our fundamental by 10 dB, the spur will drop 20 dB. So here shows a mitigation technique where I can start doing some gain, finessing into my block diagram so I can trade noise for distortion and try to come up with a cleaner spectrum. Another thing to keep in mind is with modulated signals, the spur its bandwidth will increase by the order of the RF harmonic, in this case 2. So here I'm showing that same kind of thing, a 600 megahertz tone, got 100 megahertz of bandwidth on it. The spur at a gigahertz has now got 200 megahertz of bandwidth. And if you're trying to make a measurement of a signal that's nearby, well, your spur could be masking it, so something to keep in mind. So spur mitigation techniques for the Super-Het structure. Okay, more RF filtering, both in the front end as well as in the IF. More conversion stages. I can do some spur dodging by adding more stages. And then in the gain ranging, I kind of mentioned before, so a lot more kind of optimizations to keep the mixer levels just right. And then as a designer, a lot more rigorous frequency planning when we're doing the design process. So it's hardly any frequency planning required for a direct conversion, but for this kind of a structure, you need a lot more. So I'm kind of highlighting some of the disadvantages of the Super-Het. It looks very like we're adding a whole ton of cost, size, power to this, but that was kind of, say, yesterday's information, which I'm showing on the top here. When we had low sample rate, not only was my bandwidth limited, but I was also doing things where I had to have extra conversion stages just to get my gigahertz energy down to megahertz so I could sample it. And then I also, my images were a lot closer because I'm trying to, get as wide a bandwidth as I can, and so it's putting huge demands on my filters. Well, now we got gigasample per second data converters. So now I can start my final IF can be now in the gigahertz range, so I can start eliminating whole sections of the mixers in there, and I can start doing some things where I can move some of my signals around so I can make my images further out, meaning that I get an easier filtering burden. So because of new products that are available, especially the data converters, which once a very huge burden is becoming considerably easier, actually. And so now Super-Het structures aren't quite as cost prohibitive as they once were. So the good, well, I don't get any of those IQ imbalance spurs. I don't have to do any of that calibration. And well, now that I've got higher sample rate data converters, especially, well, I'm able to ease at least the design of it, or at least make it less costly. And the bad, well, even after all that, you still get some more filtering than you would with a direct conversion type of structure. My last one I want to talk about is the single sideband. And single sideband has been used for many years in narrowband radios. And that's what's shown in the middle graphic right there. Is we have analog components that create these 90-degree phase shifts, a dual mixer type thing. And the end result is kind of shown in the graphic up in the top. Without single sideband, I get both my image and my signal of interest to both mix down to IF. With single sideband, one of them gets suppressed by, if you go through some of these equations, just the behavior of how that all works. In the past, these were analog components. We were limited to, narrower bandwidths, octave at most. And as well, we had all the parts variations, and so it was hard to maintain a lot of suppression. I've got some newer components available to me today. I've got an IQ mixers that have very wide tuning range, and inherent in there is a 90 degrees phase shift. My data converters, dual DACs and dual ADCs are becoming very common without a huge burden on price. So in the data, I can create my other 90 degrees phase shift. And now I've also got something where I only have a single mixer, the mixer stage as well as an LO. So now instead of having a multiple stage type device, I'm now back to having something that's got a quite simpler type of architecture. Okay, I said I can suppress the images, but let's see. The good is I do have some suppressed images, meaning I reduce my filtering burden. I'm down to a single conversion, single LO. But the bad is also I do still have some images. I mean, it's not perfect, so I might still have to do some, especially in the I&Q data, some kind of calibration techniques to suppress that even further. All right, so the summary. To date, vast majority of software-defined radios are use direct conversion, and it's it's done well for today's needs. But as the emerging standards is they have a lot more demands on the bandwidth as well as the increased bits per symbol. It's quite possible that the SDR architecture might have to evolve. But the fortunate thing is I'm starting to get parts that are available to me to make it such that it's not such a cost burden. And I got a couple different ideas or things to choose from depending on what the measurement needs are. And that's all I have.
Thank you, Brian. All right, do we have any questions in the audience? Okay. There you go.
Yeah, the direct sampling, is pretty prevalent in HF for, HF receivers, and then, some undersampling up to maybe 2 meters or UHF. But, scopes now, you can, I think Keysight announced a 110 gigahertz scope the other day. So there's extremely wideband data converters available, but you don't see any of it in the radio regime. Is it due to, clock stability that you need, jitter, or what's limiting it?
Probably the biggest thing is the bit resolution. Those high-speed scopes are 8 bits. We're looking at things that are 14, 16 bit type of data converters just to get the kind of dynamic ranges we want. So, there's no way we're going to get those 70 dBc type of spurious and SNRs with what we have. And then there's the cost. I mean, those scopes that you get from some of those test and measurement companies are, darn high.
Okay, Ralph?
For the transmit side, what happens at the very end in the hardware? So you have the conversions by multiplying by the 90 degrees shifted sine waves. Like what happens right before it transmits at the hardware? Because you're not transmitting those two complex signals.
On the direct conversion?
Yeah, like what happens at the very end? You just had a dot, and I was just wondering in the hardware, what's that represent?
I had a dot. It could be that apologize. This one right here?
Yeah, so in that RF out, like what happens,
Oh.
what's going on in the hardware there?
Oh,
Are you just adding them?
we'll have some amplifiers to boost up the power. I mean, coming out of the IQ modulator might be something in the order of like minus 20 dBm. So we're gonna have to put some amplifiers to boost that up to, powers that we need. And we might put some extra filter on there. Mostly, if we generate some harmonics in the RF filters, we might put a couple filters in there, type of thing. But it's yeah. It's,
Okay, yeah, thank you.
It's basic components.
Any other questions? Nope. Okay. Thank you very much.
All right.